Well, hi everybody. My name is Victor Braccichetti. I'm here to talk about value of Modelica to the building industry. And the great thing about buildings is everybody's familiar with buildings. Very approachable subject. So I'm coming from San Francisco, just a short 11-hour flight out here, but it was direct, wasn't so bad. And I work at Smith Group, so I'm in architecture and engineering company. It's an integrated firm. And we kind of work coast to coast in the United States and with an office in China as well. And we do buildings like this. So, I mean, maybe a future Modelica conference site. So this is the Virginia Tech ICAD building, the Innovation Campus Center. It's the first building on the Innovation District. The prime tenant or the key tenant is an AI tenant. And something you might find is interesting is it has building integrated PV in multiple ways. So on the shading design on the south facade of this like kind of gem-like facade. And then also on the curtain wall panels. So optimized for glare and comfort of the space. I work on the impact team, which is a national team. So I'm in buildings, but also pulled out of buildings to do infrastructure work. I work nationally. But why I'm here is talk about Modelica modeling. And I'll let you in on a secret. I've only found it about a year ago. And how did I find it? I've heard some people find it crying, like after, really tedious applications or frustrations with existing workflows. I would say frustration, definitely. What I liked about it was the really refreshing, flexible analysis capability. And the fact we can integrate workflows, whether it's Python integrated workflows or across the domains we work in, electrical, mechanical. We're also, like I said, pulled out of buildings and doing a lot of more thermal infrastructure. And it's just coupled to next generation tools for folks. So one example of how we've got pulled out of buildings, this is a kind of a new trend in the United States, are gas companies that are going from gas to geothermal with networked ambient loops. So this is like ambient temperature water being circulated between your neighbors and sharing heat. It's not an old concept in Europe, but it's relatively new. And what's new is the policy drivers that are forcing gas utilities to do this in our country. So here's an example of the first one of the first new pilots in Boston area. So in the building side, some of our typical scope would be sizing equipment, calculating energy end use. We're driven by code compliance, maybe for operational cost savings, and we also tie that into greenhouse gas emissions. That's fine. That's what we've been doing for many years. But what about the complex hybrid designs, right? So not just a single source of thermal, cooling or heating, hybrid approaches with advanced controls. How about digital commissioning of those systems so we don't spend 3 years trying to commission it and have angry clients? What about district scale, like I mentioned, and just high levels of accuracy? Maybe Modelica would be the solution. A year ago, we said, why not? Let's try it out. I did have some lessons learned from the experience of the last year. So going from industry and not from research right to Modelica, there's definitely some things to know. Well, traditional modeling tools that we use are really direct. Like you tell someone what to do, they like figure it out within 30 minutes typically. But Modelica, it's like you ever go bowling for the first time maybe, and then like the bumpers disappear, and you're used to maybe you're not a very good bowler, it's kind of bouncing around. Now that's off, so you're kind of struggling at first, right? There's not it's really flexible, which is an advantage, but also has a steeper learning curve. So some things that we do, heating and cooling loads of buildings, that's how we size the equipment, annual energy use, so dynamic simulation that captures energy use, then hydraulic modeling, and then even things like purpose-built ground heat exchanger modeling. Here's a more detailed list of the pros and cons, but really it's like the application specific on traditional modeling, like a easier learning curve. But what we like over here on the Modelica side, the flexibility it provides, and also the key thing is it's less developer constrained. So application specific tools, you have one developer. If they don't like the new feature request, you don't get it. In the Modelica space, it's easy to build new models, so we can work with multiple developers at once, including research entities. So I'm right next to the Lawrenceburg National Lab. They maintain and develop the buildings library. We're able to work with them on developing content. Our toolkit, it's the model and impact interface. And we like that because we can use open source and proprietary libraries as a mix, and a couple together. So a very flexible environment to work in. Just a quick blurb. I don't work for Model, but it could be interesting about why an industrial user would pick a certain, because I called up everybody. Demola, looked at open source, we called everybody. We like the cloud source. Some of our competition actually is using transit still, but that's like my grandfather's simulation. Basically, it's 50 years, 40 years old. We like the cloud platform in terms of collaboration within our firm, but also to our clients. And then another key thing, they come with technical support that with people that know the application, and they do both interface and library development. So you have new features that could work with you on it. So today you're going to get two for the price of one. I was asked to consolidate two case studies into one presentation, both related to building plants. So the first is kind of a traditional plant. And it was our first kind of, let's make this real, let's see how it works on a project. And it was a case where we had two different designs on a chiller plant. So if anyone doesn't know, chiller plants, providing chilled water to a building, multiple ways to do that. This was an existing large government Department of Energy site this was a campus renewal there, and they're looking at magnetic bearing chillers plus water side economizer, also called kind of free cooling, where you can just get your cooling through the cooling tower and have your compressor off. And then also a test case, what if we just remove that cost and just say, let's just use the magnetic bearing chiller only. It all started with the inputs with the cooling load. So we're able to pull building automation system data from the campus and build the cooling profile. And here's the Modelica model. This is just kind of the hard media connection, so the hydronic loops. At the top, it kind of works from the top down. The cooling load import on the top into the demand loop or chilled water loop. And then you have first the water side kind of a heat exchanger, then the chiller, and then the condenser water loop and the cooling tower, which is the backup cooling tower. In the model interface, you'd see these overlaid on top of each other, but I broke them out. So this is all the controls. This is some of the benefit we get from the Modelica, as a lot of people in this room know. This is all the kind of custom dynamic controls that we're using to engage this, make it more realistic. Including bypass for freeze protection, cooling tower fan control, condenser water pump control strategies, all being tested. Another kind of interesting thing, the most important probably parameterization was the chiller, and it's actually quite difficult to get accurate performance data for chillers. The approach we took was we spent time to get over 1,000 points at full and part load and developed regression coefficients. And one interesting thing, because Impact is Python adjacent, we're able to pull manufacturer data in, write the regression coefficients, and import it into the Modelica model to get more accurate chiller performance. What are we able to do with that? So maybe the most simple form of modeling might have a constant COP, which is coefficient of performance, basically the beneficial cooling divided by the input electrical power. So that's that blue line. But we're able to here model the part load performance, and you might be, if anyone knows chillers, it'd be like 40. That doesn't seem right. Like, we usually see 5, 6 at most for something. But at part load, it's true. I was even like second guessing the data, confirming with the manufacturer. Part load, magnetic bearing, low lift, it has amazing performance. You should capture that when you simulate. What's another thing we could do? Because it's a custom interface that we could develop our own kind of metrics. Well, how do you evaluate the system when the compressor's off? You can't just say COP, right? So we derive the total plant COP from the model. So it's the same kind of output cooling from either the heat exchanger or the chiller, but now we added like the pumps and the fan. So what's running in the system to get a system COP? And before we showed, the design CP constant, and it was dwarfed by, the part load chiller. Now the chiller's dwarfed by the when the compressor's off, you're just running a pump and a fan. We're getting over 100 COP. So very, very good performance, able to capture and kind of compare two strategies. We also had actual chiller data. So we just isolated the chiller compressor from the Modelica simulation and then compared it to what they actually ran. And we expected savings. We got about 50% against that. I mean, it was an old plant. There's probably controls issues, all this stuff, but the owner really liked to see this as like a progress update. And then if we compare the cases, the interesting thing is even though there's an advantage for the free cooling mode in the winter, based off that load profile that I showed, the cooling loads, there wasn't a ton of research-based process loads to keep the cooling kind of constant and high throughout the year. So it ended up being kind of the same. So sometimes that's a takeaway too. If you have two options and you could accurately model them and you have a comparable energy use solution at a lower investment cost, then that's also something the client's interested in. I get the same performance for less money, so we're able to do that with more confidence. Some things that matter from this, like I said, the chill performance curves, pump controls, challenging rule of thumb. We're able to test, hey, let's just run the condenser water pumps and drive the lift down. Will that actually increase energy use of the simulation, right? So that would be like a first rule of thumb for mechanical engineers or plant operators. All right, that was the first of the two. We're going to switch to hybrid geothermal decision making. Anybody familiar with geothermal pore fields? Okay, a few. This is a job that we did for a science, another government lab. And you can see all these little circles are not to scale, but bores distributed across the site. You also have to worry about the trenching cost and connecting these and manifolding them. And they're deep. I didn't mention that. So they're also deep. So, hundreds of meters, I guess, or what are meter conversions? 500 feet to 1,000 feet. That's that right there. So, a lot to coordinate, but what are the benefits? Well, very low operating costs, some of the best if we're selecting thermal sources and sinks, it's some of the best in the industry. There's no on-site gas emissions, so for decarbonization projects, we love it. There's no boilers, no water consumption like cooling towers that are used, no acoustics. Some people really love that benefit. You don't have to listen to any air-cooled equipment running, and it lasts forever, I'll say. Not quite forever, but pretty close. Longer than all of us are going to be alive. But what's the catch? Expensive, and the workflow is pretty fragmented in the design, especially for hybrid systems. Here's an example. We don't have to go through it, but basically 5 steps. Each of the little like explosions are where you break the process. You have to go to another tool. You have to kind of iterate manually. It's very frustrating. And so if you're on a project, you have all these challenges. How do you stay pumped about geothermal ground source heat pumps? So in the US, we have financial incentives that we could stack. There's sustainability goals that clients care about. We have LEED or building certifications, but also look at resilient analysis strategies, which is this hybrid workflow I'm going to talk about. So what's the challenge? You have a workflow, but you want to respond to some change, maybe in the bore field, but you don't just want to get the size of it. You want to get the so what case, the value. So that's the investment plus the energy cost or the operational value. One thing that's of interest in the US, there's a tax credit. There's other incentives too, but the key one is there's a tax credit for ground source heat pumps, and it's exclusive to that. And it could be up to 50% like coupon or discount on the whole system cost. So that's from the ground heat exchanger, all the piping down to like the diffusers in the classroom. It's a lot of money. And even if you're not taxable, you can get a checkout, so your universities can benefit from it. Pretty amazing. So how do you do the calc? Well, you have to look at the parts of the system, the ground source heat pumps in green, and the ground heat exchanger, and you have to kind of track the load, the thermal output from that. They let you do hybrid with a boiler, but only a certain amount. So, for example, you have to be over 50% from the green equipment to qualify, and then it's a prorated amount. Long story short, there's a lot of money available to kind of optimize on the hybrid amount is very important. But how do you do that? So you take the building loads, maybe, on the plant. Here we have heating and cooling. We have to have both because the ground heat exchanger is kind of a deposit bank for energy. Then we can build the Modelica simulation, import the loads, and test any kind of hybrid system that we want. And you can start to see, like, inspect visually and confirm the boiler loop is water temperature is red. The source sink kind of loop for the bore field is changing seasonally with loads. This is a year simulation. And you can even validate numerically too, which is really important. So we can take a lot of the bespoke application tools, you can't go and drill down and say, what's the temperature here, or, test pump control strategies, get the temperature off the bore field. But the bore field temperature is what drives heat pump performance, right? So very, very key. So how do we look at this? So if we look at different cases, we kind of normalize it down to the base case, and then from 1 to 8x, we just, we're going to drill 8 times deeper. How much is that going to cost? Well, it's linear. And then what's the benefit? So the first case, maybe the shallowest bore, you might test that first. I want to spend the least amount of money. So what happens? I can get the temperature off of the ground heat exchanger for the full year. This right here is kind of the red line is the limit of where you might break your heat pump. You might need a premium heat pump. So it's good to keep that in mind. So let's test another case. Maybe we're case 2 through 4, and you start to kind of cluster around something. So you can start to see diminishing returns of temperature. And then also you can see what the so what case, the energy use, which is emissions, which is cost, and kind of where you get diminishing returns in that process. The other key thing, you can track thermally, like I mentioned, each output from the simulation. So you can see how much of the year was met by the boiler, but the shallowest case is the most boiler energy, the least ground heat exchanger installed. And then what that really means is qualified energy for the tax credit. And you can start to play a game of, investment cost, how much you could get. So you can get almost to 100% with a tiny bit of boiler to handle your peak loads. But even in the shallow case, you're still getting 80%. So in this case, we're qualified throughout. And then maybe build a matrix of kind of compare these things based off of client preference or kind of weighing of what's important to them. Premium heat pumps, maybe just drive down energy use savings to hit some kind of performance goals. Yeah, so in the end, I think we're about right here in our Modelica journey. We're maybe halfway up this mountain, and there's still a lot of work to be done. There's a potential there, but we need more partners. We need more people in the industry. If I could do it in a year, anybody could do it in a year. And yeah, I think more industry tailored solutions for building level and district solutions. We have some people from the grid side that just presented. And it's really opportunity too. It's not just cost for no value. It's a chance to, jump to the next generation of tools. What's going to be a leader in the industry, and get into things that are going to be, revenue generators, maybe district scale thermal power or controls and de-risking digital commissioning, model predictive control, these kind of things. So it's really the future of the industry. Anyway, yeah, thank you.